Okay, hi. We're now on our continuation video on the principle of mathematical induction, and in this video, I'm going to give you problems that makes use of the principle of mathematical induction. So to wrap up the video before, it gives back or it draws back to the two basic steps when of what we're doing when we are proving a result by induction. Okay, so it involves two key steps, only two. Okay, so the first step is what we call the basis step. So the basis step is the one when you will verify that p of n sub 0, that is your first element, whatever your first element is, usually that's 1, is true. Okay, and next step is what we call the induction step. So this is the important step actually in induction. So we're going to assume that p of k is an arbitrary integer, that it is greater than or equal to n sub 0, is true. So we call this as our inductive hypothesis. So when p of k is true, we will need to verify then that p of k plus 1, we need to add 1 to that k, is also true. So since k is arbitrary, so in any part of the number of the natural numbers, it will also be true for all, because if k is arbitrary, k plus 1 will be the consecutive arbitrary number after that, and it'll prove true that for all, imagine adding 1 continually to that number. So it will say that it is true n for all n in n. Okay, for all n in natural numbers. Okay, for our first example, we're going to prove that 1 plus 2 plus 3 plus something 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 until n is equal to n times the quantity of n plus 1 all over 2. That will be true for all n in the natural numbers. So we're going to prove this by induction. Uh, so we're going to put it formally. So we'll say proof, and we write here by induction. By induction. Okay, so first, let's write down um, the proof that, and let's put first the property that should be there. Okay, so let's say that uh, p of n, let p of n be the statement, oops, be the statement that the summation of all I running from 1 up until n, is equal to n times the quantity of n plus 1 all over 2. Where did we get this summation notation? Remember our lesson summation notation? This is our index variable, our dummy variable. I starts in 1 because our first element here, our first term is 1 up until n. That's our upper limit, and they are said to be, if we're going to sum them up again, we're summing. That will be equal to this right hand side. Okay, so let's first write the basis step. Let's write down basis step. Okay, so for the basis step, let's verify that p sub 1 is true. So let's verify that, in our previous in our above statement, it should be p of n sub 0 is true. That's our first term. So here our first term is 1, so we will verify that p sub 1 is indeed true. So how can we verify that? So simply, that is we say here that our n sub 0 is 1. So how can we verify that? So when n is 1, we will just substitute everything here by 1. So when n equals 1, what we have, therefore, we can see that since if we're going to use 1 here, so 1, that's just equal to 1, right? Well, making 1 here, the upper limit is 1, so that's just 1 equals 1 times, substituting the 1 here in n, 1 plus 1 all over 2. So this is 1 times 1 plus 1, that's 2. So what we can see is 1 times 2, 1 times 2 over 2. And clearly, 2 over 2 is equal to 1. And this proves the basis step. Okay, so thus we can say, thus p sub 1 is true. Oops, sorry. Okay, so that's for the basis step. Let's move on the induction step. That's our step number 2. Okay, so for the induction step, oops, sorry. For the induction step, we will verify now that k is true, and then if k is true, therefore k plus 1 is also true. So we will let first k be an arbitrary, be an arbitrary ar arbitrary positive integer. So okay, so we would like to show that p of k implies p of k plus 1. So we need to show, we will show that p of k implies p of k plus 1. Okay, so let's assume that p of k is true first. So we'll start there. Assume p of k is true. Okay, so that is the summation of all I running from I running from 1 to k only. So that's the last element, k, in this example. So it is equal to k times k plus 1 all over 2. Okay, so this is what we call our inductive hypothesis. Inductive hypothesis. Okay, to show that P of k um, implies P of k plus 1, so what we will do is, so let's write, to show that P of k implies P of k plus 1, so that is, we will say that the summation of all I running from 1 to k plus 1, what we will write here on the right hand side is the um, all this case here above, but all the k's will be substituted by k plus 1 this time. So this k will be substituted as k plus 1, so that's going to become k plus 1 itself. Okay, now here, this k here will be substituted by k plus 1, so it would look like k plus 1 plus 1. So can we just make it like k plus 2 for simpler writing? K plus 2. So again, we have k plus 1 times k plus 2 all over, clearly that's 2. Okay, so we're going to tell ourselves that if this implies, therefore this is also true. So we will start with the left hand side of this equation. Okay, so we will write for the left hand side, let's put the shorthand for LHS, left hand side, is equal to the summation of all I running from 1 to k plus 1. Okay, it's just equal to the summation of all I running from 1 to k plus this k plus 1, which makes sense because what happened here is that the summation of I from 1 to k plus 1 is just equal to the summation of this all i's until k added k plus 1, because what happened here is just we just added the upper limit by 1. So what we do here is just equal. These two terms are just equal. So recalling what is the value of our summation of I for all k plus 1, this is equal to, we will start the equal sign here. This up until k is said to be equal to this one. So we're going to copy this, k times k plus 1 all over 2 here, because that's the value, k plus 1 all over 2 plus k plus 1, right? Because this value here is equivalent to this added to k plus 1. Okay, so what we're going to do is to make this equal to the right hand side, and we say that this is the right hand side. This added to another k plus 1 must be equal to this to make the induction step and the induction hypothesis true. So let's manipulate by using algebra. I think we can make this under one um, fraction bar. So using the LCD as 2, so we'll have k plus 1 times k plus 1 plus 2 times k plus 1. Okay, what we can see here then is factoring by grouping. This factor has the k plus 1, this factor has the k plus 1, what we're going to do is we're going to get the k plus 1 in each of the terms. Okay, again, this is factoring by grouping. We're going to get the k plus 1 in each of the terms. So we're going to extract that. What we have is the k plus 1 extracted. Then what is left? Here, if we're going to get the k plus 1, k is the one left. Here, if we're going to get the k plus 1, 2 is the one left. And this is all over 2. And voila, this is equal to your right hand side. Right hand side. So what we are saying here is the left hand side is equal to the right hand side. So we can conclude that if p of k is true, so is k p of k plus 1. Let me put it here. P of k plus 1 is also true. Okay, so let's finish this proof by this statement. Thus, by induction, P of n is true for every integer. So shall we for all integer n greater than equal to 1. Um, shall we put just to make it clear that these are all integers. That is the formula holds for every positive integer. Okay, and this is the end of proof. Okay, so that's it. Let me wrap up a bit what happened in this example. So in this example, we are said to prove that 1 plus 2 plus 3 up until so on, so on, so on. Notice that 1 plus 2 plus 3, these are consecutive um, numbers, okay, with a common difference of 1. If we're going to sum up all of those up until this arbitrary n, this will be equal to n times the quantity of n plus 1 all over 2 for all natural numbers. So by induction, but we'll let p of n be the statement that we want this one to be true. So the basic step, verify that the n sub 0 is true, and it is. Substitute 1 here. 1 times 1 plus 1. 1 plus 1 is 2. 2 over 2 is 1. Therefore, 1 equals 1. So that's our basic step. For the induction step, we will let k to be an arbitrary positive integer. Again, we will let k to be an arbitrary positive integer, and we'll show that p of k implies p of k plus 1, and they're both true. Okay, assume that p of k is true. So what we have is this equation. Okay, p of is summation of I for all I running from 1 to k. This is equal. We just got it from our previous statement here. We just changed all the n to k. And this is our inductive hypothesis. If it is said to be true, therefore p of k plus 1 is also true. And we have proved that here, um, which states that if p of k plus 1 is true, therefore this equation holds. And it did hold because by our algebra here, this is the left hand side, this is equal to summation of all I running from 1 to k plus 1 is equal to all i's running from 1 until only k, and then added 1, k plus 1 here. So using some algebraic manipulation, and indeed we found out that the left-hand side is equal to the right-hand side because this is the end product here. This is quantity k plus 1 times k plus 2 all over 2, which is equal to our um, assumption that it is equal to this. So indeed it is true. And so if P of k is true, it implies that P of k plus 1 is also true. And thus, by PMI, principle of mathematical induction, P of n is true for all n greater than or equal to 1, which are all integers in n. That is, the formula holds for all n in n. Okay, I think that's it for this video. I have another example, but I think that is best preserved to another video. Okay, see you next time. Bye.